record to this computer.
You have to pronounce it again after the recording starts, Nishant.
Hi everyone. Welcome to the Recurrent ETDS seminar. Today we have, to our pleasure, Professor Ángel González-Prieto, and he'll be telling us about Turing universality in dynamical systems. Over to you, Ángel.
Thank you very much. Thank you very much for the invitation to this recurrent ETDS seminar. I'm really happy to be here to deliver this talk. And the plan for today is to talk exactly about what the title suggests, about dynamical system that exhibit some kind of Turing universality. And the idea is I will explain what do we mean with Turing universality in this context. So let me start with a maybe naive but important definition.
So,
Suppose
Ángel,
that we have two.
sorry to
Yeah.
interrupt you a bit. I can see myself in your screen. You can maybe hide away that part.
Maybe now? No?
I still see myself. Yeah, now it's moving. Now it's gone.
Now it
Now it's
works.
gone. Thanks.
Thank you very much for letting me know. So absolutely. So the idea of universality is suppose that we have a certain class of dynamical systems D, and with dynamical systems here I'm thinking about smooth continuous dynamical systems. So it's a manifold M and a certain vector field Y on it, and this is a certain class of dynamical systems. And I want to say that something is universal for this class D of dynamical systems. So what is going to be universal? So it's another class U of manifolds with vector fields. And typically what happens is that U is actually smaller than D. So it's a proper subset of D. And we say that U is universal for D if you give me any dynamical system of class D, then I can find a dynamical system of class U that embeds inside it. So the idea is, okay, whatever you give me of D, maybe I have to enlarge the dimension of the element in U. Maybe I have to take a higher dimensional manifold M, but I can embed the dynamics of M inside the dynamics of M. That's the idea. Okay? And this property of universality is really important because it's telling you that obviously that the flow of Y is mapping to the flow of X. So it's like you have M with a much bigger dynamics, and inside it you find a copy of N that has the prescribed dynamics, the dynamics that you want to represent. And in particular, this means that U is as complicated as D, meaning that if you want to, let's say, classify dynamical systems in D, then you know that in particular you must be able to classify dynamical systems in U, because any dynamical system in U can be represented as a dynamical system in D. So the way around. Let me give you an example, and an example is Hamiltonian dynamics. Indeed, Hamiltonian systems are universal for all the smooth vector fields. This means that every smooth vector field can be represented as the flow of a dynamical system. And actually, the proof is very simple. Probably you all already know it. The idea is, okay, let's consider the cotangent bundle. So if you give me a smooth vector field on a certain manifold N, consider the cotangent bundle and embed N inside the cotangent bundle as the zero section. And if you consider as Hamiltonian function, just considering, okay, on a certain point of the cotangent bundle that is a position and a momentum, then take the vector field and evaluate the covector to get a number. And if you compute the equations, the Hamilton equations for this dynamical system, you realize that what happens in the zero section is literally that you are considering the flow of y inside the zero section. So this means that Hamiltonian systems are as difficult as smooth vector fields because they can be embedded, every smooth vector field can be embedded inside a Hamiltonian system. Okay? So that's the idea of universality. But
So in your
obviously
systems, there's no invariant measure that you worry about. There's nothing, no invariant probability measure or
no, I'm
so
just
you
talking
want
about
everything is smooth and continuous, in fact.
absolutely. So everything is smooth, and I'm just talking about sending flow lines into flow lines.
Okay.
That's the setting. Obviously it's a very naive approach. We will find more interesting stuff later. By the way, feel completely free to interrupt me if something is not clear. I'm very happy to answer any kind of questions. So please go ahead if I don't explain something clearly. So that's the idea. Every smooth vector field can be represented as a Hamiltonian system. But obviously you can tell me, okay, but the Hamiltonian function you took in the previous example is quite artificial because it was handcrafted to represent the dynamics. What happens if I want to consider only Hamiltonian functions that have a physical meaning? And physical meaning means that are like kinetic energy plus some potential energy. Okay, so let's not restrict ourselves to potential well Hamiltonian systems, meaning that the Hamiltonian function has this form. Okay, this gives me a smaller class of dynamical systems. I have called it UPW, potential well. Okay, are these tangent bundles, but only taking Hamiltonian vector fields corresponding to this kind of potential well Hamiltonian functions. Obviously, if you compute the Hamilton equations, what you get is Newton's law. This is second Newton's law. So here, literally, what we are saying is that, okay, the flow in U is literally the equation of motion of a physical particle in a potential field V. So that's the thing. And now the question is this class UPW universal for let's say vector fields? And the answer is no, but it's almost. There is a technical condition, and if the vector field satisfies this technical condition, then this smaller class is actually a universal. And it's a theorem by Tau that this class of potential well dynamics is universal for smooth dynamical systems, but satisfying this property, that there exists a one form that is always positive on the vector field, pointwise, and the Lie derivative of the one form with respect to y is exact. It's an exact form. And why is this needed? It's very easy to understand why is this needed. This is needed because actually these systems have this property. Because the Liouville form in the cotangent bundle satisfies these conditions. Not exactly these conditions. Here you get bigger or equal than 0, but you can actually modify slightly the Liouville form around the zeros to get strictly positive. But that's the idea. Obviously, you cannot expect to be able to reach all the smooth dynamical systems because these systems are constrained to satisfy this property because the Liouville form satisfies this property. Okay, but this is a very good result. It's universal. The Newton's second law is universal for smooth vector fields with a certain positivity property. Good, but as I was saying, this is quite naive because it's just, okay, can I embed this system inside this system? Let's do something more interesting. That is doing the same, but in a embedding in an infinite dimensional manifold. So let's consider the infinite dimensional potential well. And the idea is, okay, I want to consider the same potential well equation, but I want to add this term. So U is now a function both of time and some spatial coordinates that are periodic. And now I want to consider this equation that is the same equation as Newton's second law, but with this extra term. And it turns out that this equation can be got as the Hamilton equations of a certain Hamiltonian system, but on an infinite dimensional manifold. So we have to consider the infinite dimensional manifold of C infinity functions on the from the torus to M and from the torus to M twice. And the idea is I want to consider the Hamiltonian function that repeats the same trick, but now now what you get is a function on the torus, and you integrate this function on the torus. Okay, so that's the idea. You repeat the classical potential well, but in this infinity dimensional setting in which you have this manifold that is infinite dimensional, and you can consider this infinite potential well dynamical systems, this U infinity PW, and it turns out that Tau also proved that this class is universal for exactly the same type of dynamical systems. C infinity smooth vector fields with this producitivity property that there exists a one form that is positive from the vector field, and the Lie derivative is exact. So this is good. This means that, okay, let me draw something. This means that, okay, I have my super big M, curly M, and it says the following. If you give me, this is like super large, the green thing, and if you give me something not so large, here, M, that is finite dimensional with a certain vector field Y, I can embed this into this, so that here I get in my infinite dimensional manifold, I get a copy inside of N, and the flow on M restricts to this flow of N in these slides, in this submanifold. Okay, so considering universality in infinite dimensional setting, in the infinite dimensional setting, makes sense, makes a lot of sense, and actually it's something that you can do if you want to understand how difficult are the solutions of a certain partial differential equation, like this one. Now you know that solutions to this PDE are as difficult as smooth vector fields with positivity property. Yeah, and in particular, this is particularly interesting for Euler flows. So Euler flows, the Euler equations are given on a certain Riemannian manifold. So let's consider a Riemannian manifold, and the Euler equations are these equations. So you get a time-dependent and volume-preserving vector field, and you consider the equation that says the time derivative of the vector field plus the covariant derivative with respect to the Levi-Civita connection of G of X with respect to X is equal to the minus gradient of a certain prescribed function that is the pressure. So these equations actually model the motion of a perfect fluid with no viscosity moving in M and when constrained to the pressure P. And obviously these equations are very, very difficult. In particular, it is not known whether this equation have blow up or not. So it will be interesting to get some ideas about how difficult, how involved are the dynamics of these Euler equations. And actually, Tau gave the very first step in this direction, proving that they are actually very difficult, proving that Euler flows are universal for quadratic ordinary differential equations. And let me state this properly. So it says, let us consider a quadratic form. It's actually not a quadratic form. I'm slightly lagging here. B, what B is here. It's a map from Rn times Rn to Rn, such that component-wise is a bilinear form. Okay, and suppose that it satisfies this property, so that you have, this is the standard metric in Rn, and it satisfies that is orthonormal to itself. Let's say it's a quadratic form. Then there exists a Riemannian manifold n, and an embedding of Rn into the space of vector fields on n, such that if you give me a solution of this quadratic ODE, then the image of this map is a solution to the Euler equations.
So,
So
Angel,
that's sure.
I have a question.
Sure.
So, when we say that, these, the nature of solutions of these Euler equations is equally or is at least as hard as solving these things. So, what is the nature of this embedding? So, for instance, is this explicitly given? Is this computable? Like those are.
Absolutely. Thank you very much for asking this question, because actually this embedding is the best you can expect.
I see.
It's linear. It's a linear
Oh,
embedding.
right. You have already said linear. Yes.
So this embedding is actually is constructed by constructing n solutions to the Euler equation and saying, okay, x1 xn is set to the splitted n solutions to the Euler equations I constructed, multiplied by the corresponding constants. So it's super split, and actually the solutions are quite split. The only thing that is not so split is the metric. Here I'm lying because it's solution to Euler for a certain Riemannian metric, and the metric is somehow handcraft, and it's constructed using partitions of unity. So it's not, I mean, it's understandable. There is a formula, but the formula depends on some partitions of unity, some extensions.
I see. So, given that, we are thinking about Turing machines and so on, are these embeddings computable explicitly? Like, can you get to a close enough approximation in a reasonable time and so on?
So again, a very good question. We will reach this idea of Turing universality in a minute, but the idea was that, okay, when Tao proved this theorem just by trying to prove that the Euler equations are very difficult, and are very difficult because they represent quadratic dynamics.
Quadratic, yeah.
Quadratic dynamics. And then he thought, and this was the starting point of a very, very interesting program. He thought, okay, if I can manage to represent any quadratic flow, can I represent any Turing machine? Saying like, okay, instead of considering quadratic flows in Rn, I want to consider Turing machines in a certain sense as a discrete dynamical system, and we will talk about this precisely in proper terms in a minute. Can I repeat the same trick? Am I able to embed the discrete dynamical system corresponding to a Turing machine inside the Euler flow? That would imply, and the idea was precisely to say, okay, I will use this to prove that the Euler equations have blown up. Because now I create a program, I create a Turing machine that blows up, like self-destroys. And in that case, what the thing that I do is I say, okay, I will embed these dynamics inside my Euler equations, and since the dynamics of the Turing machine explodes, then the Euler flow explodes. That was essentially the idea. Observe that this approach, even though it's very interesting, it prevents blowing up precisely because of this condition. This is a kind of energy preserving condition, and since you have this energy preserving condition, actually you can prove that these quadratic vector fields do not blow up. But that was the idea, to repeat the trick, but with a computer, whatever that means. Yeah, clear?
Yeah, thanks.
You're welcome. So, in short, Tao's theorem actually says that Euler flows are universal for quadratic flows satisfying this property. And as I was mentioning, the embedding is super explicit. You get a bunch of n solutions to the Euler equation that are very explicit, and a solutions of the Euler equation for a certain metric that you handcraft. Okay. More results about universality. There are many results about the universality of Euler flows. Let's say Paco Torres de Lizaura actually proved that Euler flows are universal for polynomial vector fields on Rn that are tangent to the sphere. And this is very nice because this implies that Euler flows are chaotic, because you can construct chaotic flows using polynomial vector fields with this property. So using this idea, he proved that Euler flow is chaotic. And also they proved, Robert Cardona, Eva Miranda, Daniel Peralta Salas, and Fran Presas proved that steady Euler flows, meaning that the vector field is time independent, so the time dependent term vanishes, are actually universal for non-autonomous Euler flows. So studying the steady Euler equation is the same as studying the non-autonomous Euler equation. And so it's a good idea to focus on solutions of this, which are vector fields with no time varying. Okay? And that's the moral. That universality must be understood in a much more broader sense. This is a property of being able to embed a dynamical system into another, maybe infinite dimensional and maybe discrete, in the sense that I'm going to say in a minute. But that's the idea. Universality is much more broad than the definition I gave at the beginning of the talk. That was embedding, blah, blah, blah. No, it's the property of representing, embedding something inside a bigger class. And what can we do for discrete dynamical systems? For a discrete dynamical system, what we can do is, okay, give me a discrete dynamical system, let's say, and I want to consider, let's say, continuous maps, that's all, not necessarily diffeomorphisms. If you give me a continuous map from a manifold M to N, how do we say that we have embedded it into a continuous dynamical system? If I can do the following. Suppose that I manage to construct a bigger dimensional manifold here with a flow, and I can do the following. For this flow, for this ambient flow, I can find a Poincaré section, meaning that a small disk, or in this case, a copy of M, with the property that if the flow starts on M, then it will flow around the manifold, but it will come back, and at the first time it comes back to M, I call this the Poincaré return map of the point. This defines a discrete dynamical system on this Poincaré section, And the idea is I can represent a discrete dynamical system if I can represent it, if I can recover it as the Poincaré return map for a certain vector field and for a certain Poincaré section. So that's the idea. And the question is, can I do that? Can I embed any dynamical system? Well, the solution is yes, and there is a missing thing here, if phi is smooth. Why? Because if phi is smooth, then I can consider the mapping torus and the Poincaré section m times 0 such as Poincaré return map literally phi. So if phi is smooth, then I can do it. But the interesting discrete dynamical systems will be exactly those in which phi is not smooth, as Turing machines. And let me explain this in a minute. But that's the idea. That's the idea. I want to consider I want to consider dynamical systems, and I want to do this trick. But in any case, this trick of the mapping torus will be very useful in a minute. Okay, so that's the idea. If you give me a smooth thing, then I can embed it as the zero section of the mapping torus, of its mapping torus. And if phi is null homotopic, so it's homotopic to the identity, this mapping torus is actually m times 0, 1. So it's much better. M times S1. So it's much better. So, okay, our favorite discrete dynamical system will be Turing machines. Turing machines. And what do we mean with a Turing machine? And let me explain why a Turing machine should be understood as a discrete dynamical system. So a Turing machine, in proper terms, is a mathematical model of a computer. And the idea is that it is represented as a set of states, Q. So we have a finite set of states, Q. A certain alphabet that here is a binary alphabet, 0, 1, and a blank character. So this is just blank, like the empty character. Nothing is written here. And we have a transition map. And the transition map says the following. If I am in a certain state and I read a certain symbol, then I will change my state to another state. I will write another symbol and I will move. Let me explain this with an example. Suppose that we have this Turing machine. So the idea is that the Turing machine is this head. This is a writing head that has some internal state, here Q1. And so this is like the CPU of our computer. And this CPU is reading a memory, and the memory is this tape. It's an infinite tape, but this tape is forced to be blank eventually. So only a finite number of symbols are written in the tape. And at every step, the Turing machine, the CPU, is going to read a symbol, this symbol. It's going to read a symbol and it's going to say, okay, I am in state Q1 and I'm reading the symbol 0. So, and apply you apply the transition function, and then you get another state, meaning that, okay, I'm going to transition from state Q1 into state Q2, another state of my finite set of states. I will write another symbol. So suppose that we have that, in this case, delta of Q1 0 is, let's say, Q2 1 minus 1. Q2 means that I'm transitioning to state Q2. 1 means that I'm going to replace this symbol by a 1. And minus 1 means that I'm shifting to the left. So now the head will be here. And the next symbol to be read is this one. So that's the way a Turing machine operates, and it's literally what a computer is doing. At any step, the computer is reading the memory, making a decision in terms of the internal state of the CPU and the piece of memory that you are reading, and then you change the memory by another piece of memory, and then you move. So it's an abstraction of a computer. And several observations are in order. The first one is that obviously we can change the alphabet. Here I'm focusing on the binary alphabet because computers are binary, but obviously you can do the same trick with a finite alphabet with finally many symbols, and the same works. So it's perfectly doable with more symbols. But the only important thing is that the tape, the initial tape, the memory has to be eventually blank, meaning that only a finite number of symbols in the memory are written at the beginning of the calculation. That's the idea. And the Turing machine continues doing the operation and doing the operation and doing the operation. And at some point, the Turing machine can halt and say, okay, I'm done. And this is the result I give you in the tape, like a computer. You have a computer, you write in the tape, you write in the memory 7, and you say, okay, compute the logarithm of 7. And then the computer starts doing some calculations. And when it halts, it says, okay, now in the tape, you have the logarithm of 7, the result of the function I wanted to compute. So that's the idea of a Turing machine. And how can we understand a Turing machine as a dynamical system? Because it's a dynamical system. How? Consider this thing. This is it's called the state space. State space. So it's possible states in which the Turing machine can be, and these are finite strings of symbols of A. So possible contents of the tape. And what happens is that a Turing machine defines a discrete dynamical system from the state space to the state space. If you give me you are in a certain internal state, and you give me a certain tape, I will give you what is the resulting internal state and what is the resulting tape. Okay?
Sorry, I am a
Sure.
little confused. So if you give me a certain state and you give me a word in the tape, don't you also have to give me a position, or are you assuming that the Turing machine will halt, and therefore you're telling me the result of the entire computation?
So thank you very much. So the point is the following. Here I'm being sloppy. A star are two-sided sequences.
Sure.
So are sequences that may have negative indexes or positive indexes, and I'm supposing that the head of the Turing machine is always at position 0.
I see.
And the thing that is shifting is the tape, is not the head. Okay, it's easier to explain the thing as thinking that the thing that is moving is the head, but you can alternatively think that the thing that is moving is the tape, and the head is always at position 0. So here, the head is always at the 0 position, and an iteration of this the discrete dynamical system is one step in the Turing machine.
I see. And so there's no reason to assume then that the word is finite, right? It would work as well for an by infinite word. Like you don't need blanks on the ends a priori.
Sure. But the thing that happens is the following. If the Turing machine halts, it has been only able to read finally many symbols in the tape.
Right. So it doesn't matter. I see.
It doesn't matter, exactly. That's the thing. It doesn't matter. But it's better to think that the tape is written only in finally many symbols, because the Turing machines that you care about are those that halt, and those that halt are only able to read finally many symbols.
Okay.
So let's say without loss of generality, we can think that the tape has finally many non-black symbols. Yeah. So that's the idea. We have this discrete dynamical system, and it's a Turing machine gives you a discrete dynamical system like this. And actually, Moore in 1991, he proved that this dynamical system is actually very well understood because it's a generalized shift. And a generalized shift is the following: is on the set of strings, two-sided strings, and is the following: a generalized shift is determined by a window size. Here the window size is 2, and the thing is that a generalized shift always takes the string, reads the window size, in this case 2, and makes a decision in terms of what he have read. So I have read 0, 1, so I will substitute 0, 1 by 1, 0. Perfect. And then I will shift a certain amount of positions. Here, 2. So I will shift 2 positions to the right. So that's the idea of a generalized shift. It's a discrete dynamical system determined by a fixed window size, here 2, and for every possible window size, for every possible sequence in the window, it does 2 things. First, substitute the thing that you have in the window by another string, and then shifting a certain amount of positions. So it's a generalized shift because it can move more than once, and it substitutes many symbols at the same time. And Moore actually proved that this thing is equivalent to a generalized shift on the set of possible strings and on the symbols. And you can tell me, but what happens with the states? Because you are getting rid of the states. And I don't want to go into the details of the proof, but the idea is you encode your state inside the memory. So you encode your state inside the memory, and that's the reason why you have to increase the window size, because the window size contains both the symbol that you are reading and your state. That's the way you prove it. You encode your internal state inside the tape, and the window size allows you to read both information. Okay. So
Can you go back to your previous slide?
sure. This one.
Oh, no. Next slide, actually. The slide you're actually dealing. So
Esta.
I just want to make sure I understand the generalized shift. So generalized shift is a map from A star to A star, but it's highly non-continuous, right? Discontinuous, because something very far away could affect how my map acts upon, because you're reading the entire word and then you're deciding how to change the word. While
Sure.
you
Sure. So I mean, I haven't said what is the topology that I want to put here. So
True.
I cannot say what does it mean to be continuous. But the thing is that it should be somehow continuous for the following reason. It should be continuous because it is only affected by finally many symbols. It's true that then I'm shifting, but if I have a certain topology that says, okay, things that are far away doesn't really matter if they are just shifting, then it will be continuous in this topology.
Absolutely. So I see. So a generalized shift is a map on A star where there's a fixed window size on which you transform. I see.
Exactly.
Okay.
So
I think I understand.
actually, I can give you the precise definition. So a generalized shift is a triple W, which is the window size, F and G. And F is a function from AN, so it reads N symbols and gives you another N symbols that are the symbols that you are going to substitute. And G is a function from AN, it reads the same symbols and is going to give you a integer number that is the amount of
shift.
shifting. And that's
I
all.
see.
And with
I
these
see.
3 pieces of information, you get the generalized shift.
Okay. Very, very nice. All right.
Okay. Thank you very much. So the question, the important question now is, given a class of continuous dynamical system, can I embed a Turing machine in it? Can I embed these generalized shifts on it? That's the question. That will mean that the continuous dynamical system is Turing universal because I can represent this discrete dynamical system. But I'm going to be even more precise because, okay, you can say, okay, this dynamical system happens on A star. A star is very crazy. I don't understand it very well. So let's describe this as a discrete dynamical system on a very familiar space. That is a disk. And there is,
Can I
sure,
ask you another question? Sorry, I'm
absolutely.
asking
No, no,
many,
no,
many
no,
questions.
no. That's very good. Thank you very much.
So what happens if the system halts? If your Turing system, you have so Turing machines which halt, you don't worry about them at all. All your Turing machines run for infinite time.
Oh, well, I can say this in two different ways. A Turing machine will halt if and only if it finds a fixed point here.
Right.
So when it halts, you reach a fixed point. And if it doesn't halt,
I see.
I don't reach a fixed point.
Okay. All right. So it's a semi-group instead of a group action.
Exactly.
Okay.
Yeah. So that's important. That's important. We are saying that the Turing machine is halting if when I apply the discrete dynamical system, I get the same thing because it halts. It keeps the same state. Okay, so how can I make this much more precise? Well, it turns out that I can embed this state space. Actually, I can embed this A star, this space of two-sided sequences inside the Cantor set, the square Cantor set. And the idea is, okay, if I could have binary sequences, then since the points in the Cantor set are binary points such that the binary expression have either 0 or 2, then every time I have a 0, I embed it as a 0 position in the Cantor set. Every time I have a 1, I embedded it in as a 2 in the digital expression of the binary expression of my number. So that's the idea. I encode this into the Cantor set, and I'm considering the square Cantor set because I need two Cantor sets. One to represent the positive numbers. So the idea is, okay, I consider this part of the tape. This part of the tape, I read it as a binary expression of a number, and I take this number in the Cantor set. And I do the same trick with this other part, the negative part. I do the same trick. I get another number in the Cantor set, so I put this pair of numbers as a point in the set. So I can embed S, this space of states, into the square Cantor set that is inside the square, the two-dimensional disk, standard disk. And actually, Moore proved that you can extend this discrete dynamical system so that it becomes conjugated to a volume-preserving diffeomorphism of the disk that is actually very simple. I call them blockwise diffeomorphisms. Blockwise diffeomorphisms. In the following sense, the operation is the following. This corresponds to 4 blocks of the square Cantor set. Let's say these are the numbers that start with 0 in the binary expression, and these are the numbers that start with 1 in the binary expression in the x-axis, and the same happens in the y-axis. And then the map is able to move these Cantor blocks into another set of Cantor blocks, like A goes to this block. And this block also corresponds to points in the Cantor set that have some property that you prescribe how they start. Like, let's say in this case, probably these are like you don't care. Here is you don't care about the binary expression of the positive part, but then the binary expression in the negative part, that is the one that is encoded in the y-axis, has to start with 0 that's the reason why it's in this part, but then 1, because that's the reason why in this part is in this part. So these are the sequences that start with 0, 1, whatever. So the diffeomorphism does exactly this. It has a finite number of fixed blocks and a finite number of fixed blocks in the image, and it sends the blocks to the blocks, being volume preserving and the identity at the boundary. These are the block-wise diffeomorphisms of the disk. And now the reformulated Turing universality now is crystal clear. Given a class of dynamical systems, is it possible to find an embedded disk that is a Poincare section and such that the Poincare map is any generalized shift, any of these things, any volume preserving block-wise diffeomorphism of the disk? So now the question of Turing universality is crystal clear. Can I find, let me repeat it because it's very important. Given a dynamical system, continuous dynamical system, can I find a Poincare section that is actually a disk such that the Poincare return map on this Poincare section is exactly this volume preserving diffeomorphism of the disk? That's Turing universality. Because you are representing the operation of a Turing machine in your Poincare section.
So
Questions?
yeah, so you started your Turing machine, then you embedded it into this map on Cantor systems, and then this,
Sure.
yeah, and that you're further embedding inside volume preserving map on the disk, diffeomorphism of the disk. Yes.
Exactly. And the important thing is that if you give me one of these, but now it's a purely mathematical geometric question. Can I embed these block-wise diffeomorphisms of the disk as Poincare return maps of certain dynamical systems? And obviously, if you give me a block-wise diffeomorphism of the disk, I have to construct a certain continuous dynamical system, as it happened for the naive Turing universality, that if you gave me a smooth vector field, I constructed a certain Hamiltonian system. Here is the same. If you give me a certain block of this, I will handcraft a continuous dynamical system that represents it as a Poincare section. Yeah. More
Cantor,
questions, comments?
is the Cantor set that you get, is it an attractor for this dynamical system, or
It will depend on the nature of the Turing machine, in the sense that if the Turing machine, for instance, doesn't halt and just shift to the right, let's say, then you get no attractor at all because you are moving all around the Turing, the Cantor set. So it will depend on the dynamics of the Turing machine. It will totally depend on the dynamics. Yeah. So the most important theorem in this regard is this theorem that says three-dimensional steady solutions of the Euler equations are Turing universal, meaning the following. If you give me one of these block-wise diffeomorphisms of the disk, I can construct a manifold M with a certain Riemannian metric G, so that you consider the solutions to the Euler equations here, and I can find a solution to the Euler equation, so a certain vector field here, with the property that there is a Poincare section. Oops, I want to use green. There is a Poincare section, and the Poincare return map on this Poincare section is literally the given Turing machine, the given block-wise diffeomorphism of the disk. And how do you prove it? Well, let me give you the most important ingredients. Well, this is a theorem by Robert Cardona, Eva Miranda, Daniel Peralta Salas, and Fran Presas. And let me explain you what are the key ingredients in this proof. The first key ingredient are Beltrami fields. So Beltrami fields are eigenfunctions of the Karl operator. They are not literally eigenfunctions because are vector fields such that the image under Karl is the same vector field with a certain factor, but the factor may vary. So it's not a fixed number, so it's not an eigenvector, but it's like an eigenvector, but with varying constant. But always positive, always non-zero. These are called Beltrami fields and are very important because it's quite easy to prove that they are stationary solutions to the Euler equations, but they are very flexible. So they are a specific subclass of solutions to the Euler equations that have been used many times to prove properties. Like maybe you have heard that there are solutions to the Euler equations that have any node as flow lines. Then you do this using Beltrami fields. And actually, the key tool with Beltrami fields, the key reason why they are so important is because there is the so-called contact mirror that says that actually one of these Beltrami fields is equivalent to giving a contact structure. So let me rephrase very quickly what is a contact structure. It's a plane distribution that is non-integrable. But in terms of forms, this means that you have one form on your odd dimensional manifold. Contact structures only exist on odd dimensional manifolds, with the property that alpha wedge d alpha to the nth power is a volume form. It's a volume form. And if you have one of these contact structures, you can define what are called the Rev-like vector fields, that are vector fields that vanish d alpha. So they are vector fields that are transverse. So alpha defines a plane distribution as its kernel, and R is transverse to this distribution. Okay, and this property is that this plane distribution is highly non-integrable. And the contact mirror is literally that X is a rotational Beltrami vector field for some metric if and only if it is Rev-like, so it's transverse to the contact distribution for some contact structure. And this is the contact mirror. The proof is actually very simple. Like I can do half of the trick. Like suppose that you give me a vector field X with a metric G that makes it a Beltrami field. Then consider the dual one form, and now you compute. And by definition of Karl, literally what happens is that the hot start of the alpha is G of the Karl, but the Karl is f of X. So this is f, you have f here, and then you get Gx, and this is alpha. So you get that star d alpha is some positive factor times alpha. And then if you compute the contact condition in dimension 3, that is L equal 1. Here, what you get is alpha wedge the hot star of alpha, which is positive, multiplied by this factor that is positive. So alpha defines a contact structure. And the reciprocal is kind of similar. And then you are done. Because once you have this co-symplectic mirror, you can prove this very easily. This idea that 3D STD solutions of the Euler equations are Turing universal. And let me give you a sketch of the proof. Give me a Turing machine, or in other words, give me the symplectomorphism. Well, give me the volume preserving map of the disk that represents it through Moore's theorem. Since it is a volume-preserving map in dimension 2, volume-preserving maps are literally symplectomorphisms because the only important information is the volume form. Okay, so this is a symplectomorphism. Now I consider the mapping torus. As I said before. And in the mapping torus, what happens is that, okay, I get a new dynamical system, and the zero section is, so the zero section is a Poincaré section, and the return map is literally phi. So this mapping torus is good because it's part of the data that I want, and actually admits a contact structure. Why? Because this map is a symplectomorphism, and if you are familiar with contact structures, they are like suspensions of symplectic structures. So it's very natural that it admits a contact structure. Now observe that actually this mapping torus is not very crazy, because phi is the identity at the boundary. And since it's the identity at the boundary, is null homotopic. So this is actually D2 times 0, 1, diffeomorphic to D2 times 0, 1. So it's a solid torus. It's a solid torus. Well, it's D2 times S1. Yeah, so it's a solid torus. And now you can embed this solid torus inside any three manifold, literally by using a certain closed path. And then you extend the contact structure. And by this theorem, this contact mirror by Navier and Geist, you get a Beltrami field. Because you have a contact structure on a three manifold and on a given three manifold, and then this means that you get a Beltrami field, and this Beltrami field is a solution of the Euler equation. And inside this mapping torus, the Poincaré section is the given phi. Is it clear, the idea of the proof? Yeah. Cool. And very recently we have extended this theorem. I promise I will finish in 5 minutes. Is that okay to finish in 5
That's
minutes?
fine. We started 2 or 3 minutes late, so please go ahead.
Perfect. So actually we have very recently extended this proof to a much more difficult setting, which are the Navier-Stokes equations. So Navier-Stokes equations are the same equations, but you get an extra term that takes into account the viscosity. So now it's a fluid, but the fluid has certain viscosity eta. And the problem is that you wouldn't expect the Navier-Stokes equation to be Turing universal, to have this property of embedding Turing machines, because they have dissipation of energy. Like this term tends to dissipate energy, so it's like you have a computer that is losing energy, so you wouldn't expect to have Turing universality, but you do. You actually have Turing universality. And let me give you very briefly the idea. Instead of considering this co-symplectic mirror that relates rotational Beltrami fields with contact structures, you use a co-symplectic mirror that relates harmonic vector fields with co-symplectic structures. Well, that is a different kind of structure on your manifold. And harmonic vector fields are super nice because they are known to satisfy the Navier-Stokes equation for any viscosity. And it's very obvious. They are harmonic, and the term with the viscosity is the Laplacian. So this term vanishes. So actually it's like cheating. You are actually solving the Euler equation, but you can get rid of the viscosity term in the Navier-Stokes. But obviously harmonic vector fields are much more rigid than Beltrami fields because they are harmonic, so they satisfy minimum energy and this kind of stuff. So the same happens with co-symplectic structure. And a co-symplectic structure is somehow the perpendicular thing to be contact. In the contact setting was a one form such that when you weight it with its differential, you get positive. Here is you have two one forms, alpha and omega, two forms. Alpha is a one form and omega is a two form. Both are closed, but the weight of both of the two is a volume form. So omega plays the role of d alpha, but d alpha is zero in this setting. Okay, and using the same trick and the same kind of ideas, you can prove the co-symplectic mirror, and then kind of mimicking the proof, you can prove the same thing for Navier-Stokes. But it's actually much more technically involved because harmonic vector fields are much more involved. In particular, co-symplectic structures are much more rigid than contact structures. Contact structures exist for any three-dimensional manifold. Co-symplectic structures do not. Okay. And a friend of mine, Eva Miranda, always explains this with a case that was a cargo that was carrying some rubber ducks in the 90s, and the cargo sank here in the middle of the Pacific, and the rubber ducks were dumped to the sea, and they started moving around following the flow of the Euler equation, the Navier-Stokes equation. And all the scientists started studying the flow and predicted, oh, don't worry about it. All these rubber ducks will appear here in the West Coast in a month or something like that. So they were there trying to collect the rubber ducks, and this doesn't happen. Only a few appear here, and what happens is that the rubber ducks were spread all around the world. They appear in Australia, in Europe, in the East Coast, so it was completely crazy, and it's precisely because of these super crazy dynamical systems that are Turing universal, and in particular are undecidable. Okay, I just want to give a super brief idea of another thing that we have done very recently, and is this idea. We have repeated the same trick of embedding Turing universality, but instead of looking at representing Turing universality as a Poincare section, we want to do the same thing but as a bordism. So we want to consider a bordism. So it's a manifold, a three-dimensional manifold that has two boundaries. So it has two boundaries, that is this disk and this disk. And the thing that I want to do is I want to find a flow that starts on a point of the Cantor set that represents an input, and then the flow do some crazy things in the middle, but it ends with another point, and the thing that I want to do in this point is to be the result of executing the Turing machine. So if you remember, in the previous setting, Turing machine, one step in the Poincare map was one step in the Turing machine. Here, what I want is that when I reach the outgoing boundary, I get the final result of the Turing machine. And we recently proved that this can be done for any computable function. Here it says any computable function, so any function computed by a Turing machine. There exists a bordism that has this reaching map, the hitting point of the flow, to be the computable function. And the idea is to consider the Turing machine as a graph with some states and some transitions, and enlarging this graph to get a bordism. And this idea gives you the flow. And I think that's all. I have details about the proof. If you want details, let me know, and I will be happy to explain it. But that's the idea. That's the idea. This gives us many new things to do. Like, okay, in the previous case, we talk about solutions to Euler, solutions to Navier-Stokes. Can we repeat the trick with other kind of dynamical systems, other kind of PDEs. We have new interpretations of universality, both using these Poincare sections, but also using these dynamical bordisms. These dynamical bordisms draw inspirations from quantum field theory, that is the idea of having bordisms and gluing them. And actually, this idea of using dynamical systems to represent computation opens an important question is, can we beat the quantum supremacy, in the sense that can we create flows of dynamical systems that compute, but actually compute faster than any Turing machine? So can I get a super crazy bordism so that the map that I get computing a certain function is quicker than any Turing machine, and is even quicker than any quantum computer? That would be like a dream. And I think that's all. Thank you very much for your attention. And if you have any
Let's
questions
thank
or
the
comments,
speaker.
thank you.
Questions. There were plenty in the talk, but yeah, some more.
I can just say, while you are thinking your question, that this is actually an image generated by ChatGPT with a prompt. Give me a picture of a computer that is made of water. So it's a water computer. That's the reason why the tape is like a waterfall, and the memory is like a waterfall, and these things is like water flowing. So that's the idea of creating computers using solutions of the Euler equation.
So, one question I had, Anil, so usually when you're doing these embeddings, it's something about particular points which will, for instance, it was this Poincare return map for certain sections. The rest of the dynamical system can be quite wild, right?
Absolutely,
It can
absolutely.
be.
Absolutely. And it makes sense that is quite wild,
Mhm.
because actually, if we come back to the very first example of the talk, that was the Hamiltonian
Right.
smooth thing, what happens is that, okay, in the zero section, you get your vector field,
Hmm.
but outside the zero section, the system can be super wild. So that's the idea. That's the
Mhm.
reason why you expect that the Euler equations are even more involved than Turing machines, because only looking at a certain small part, you get a Turing machine, and the rest is even wilder.
So, for instance, suppose what are the kind of questions one can expect to answer using this? Some more questions which one might want to answer. For instance, I might want to answer the question that in a manifold, if I'm given a point, I would like to understand what its orbit behaves like. And are you saying that this is going to tell us that all non-trivial properties of this orbit are undecidable or something of that sort? Is this
Exactly. So,
that's the
very good point. So, one of the key, I haven't mentioned this, but one of the key problems in Turing machines is
hmm,
that the halting problem is undecidable.
right?
Meaning that if you give me a Turing machine and an input, there is no algorithm able to determine whether the Turing machine will halt with this input or not.
Hmm.
And this implies that determining whether a solution to the Euler equations in a so you have a solution of the Euler equation, and you want to understand whether this solution will cross this area, this zone of the manifold or not. That is, I have a solution starting in a certain point of the Poincare section, and I want to check whether it will cross the halting part or not. This is
Hmm.
undecidable. It's undecidable to know whether a solution of the Euler equation will cross a certain zone or not. And obviously, and that's the idea, all the theorems you have about Turing machines,
They'll have some,
they have some counterpart, dynamical counterpart.
right. So if one looks at, say, complexity for Turing machines, what would be the counterpart in
So that's a very good idea. So suppose that you want to consider a Turing machine solving some certain problem, and this problem has some complexity class. This implies that okay, so this certain some complexity class, and you know that it cannot be solved more efficiently. This means that there is an Euler flow that to reach a certain area, it requires
certain amount
enough,
of repeat?
exactly, certain amount of iteration. It cannot reach this area very quickly
Right. So it's
because
sort of,
otherwise,
yeah, so it's sort of capturing the recurrence of the point in the point intersection, the recurring times, the
exactly,
visit times in the point.
exactly. What happens is that you have a discrete dynamical system with the properties of the discrete dynamical system inside a continuous dynamical system,
I see.
and all the properties of the discrete dynamical system transfer to properties of the continuous one.
Sorry, I have really asked too many questions. Anybody
No,
else?
no, no.
Sorry
No,
about
I
this.
think you covered for all of us. So maybe somebody else, Dipanshu, I guess. Yeah.
Hello, Professor. Yeah, thanks for the talk. Yeah, it was a really nice talk. So I have just, I just want to know something like a generalized shift when you're defining generalized shifts. Yeah, can you go to? Yeah,
So,
and you define a function g from a n to z. Is it a bounded function or unbounded function?
it's a bounded function because an is finite. Because A
So,
is the alphabet, so it's three symbols in our case, and rise to well, I said N. Sorry, N is not N. It's W. Is the width size, the width of the window.
So when you like we have a window of let's 0 1, so we have window of two symbols like two blocks, and when you're shifting it to the right, so we can just shift to two places, right?
No, I mean we can shift as much as we want, but if we have W equal 2 and A equal 0, 1 and the blank symbol, then
Mhm.
this guy has 3 square, so it has 9 possibilities. So it's a function from 9 points to set. So okay, maybe I can move 1,000 to the right, but that's all. So like since there are only finally many possibilities here, the amount of shifting that I can apply is bounded.
Okay,
I can move. I can shift 1,000 if I want. That's perfectly doable. I'm
but
not restricted.
it should be a bound. There should be a bound, right?
There should be a bound, but the bound is because this set is finite.
Okay,
Sure.
okay, thank you.
You're welcome. You're welcome. Thank you very much. That's a very important point. That this generalized shift operates on finite. Actually, this generalized shift is typically given as a table that says, okay, when you read this, you are going to write this and move this. When you read this, you are going to do this, and so it's a table. It's like a lookup table because it's a function on finally many strings. Yeah, thank you very much because that's crucial. That is a very small amount of information.
And just small questions. Have
Sure.
you taken the function subjective or it's just a continuous?
This one, you mean? Which one?
When you're defining like any dynamical system can be embedded to turn a machine, right? You're saying so.
You mean this embed? No, for sure. This embedding. is typically injective, but is not surjective. Typically, you are embedding n inside a much larger dynamical system. That's the reason why there is an outside that is wider. And you have control on the submanifold n, but you don't have control outside n at all.
Okay, and also when you're relating this dynamics and discrete dynamical system, so you have taken a discrete systems. So
Here, yeah.
yeah,
So
so this phi system from M to M, is it onto, or it is just continuous?
you don't need to be onto. It might
It is
be
not need to be onto.
any function you want. Typically, if you want to do the mapping torus trick, it has to be a bijection. It has to be a diffeomorphism. So if you want to do the mapping torus trick, you need this to be a diffeomorphism. But if phi is not a diffeomorphism, the question makes sense. Makes
Okay.
sense. Actually, even more interesting, it also makes sense for partial functions. So say, okay, you have a function that is undefined on some points of M, and these points of M corresponds to starting points in which there is no Poincaré section. The flow never comes back to the Poincaré section. So it also makes sense for partial functions.
Okay. Okay. Thank you.
Thank you very much.
Other questions? Okay, thanks a lot, Angel. This
Thank you very
was
much.
I'm very glad to have you here.
Thank you very much. Thank you very much for the invitation, and thank you very much for the question.